Hey, hello everyone. Today, we're going to go through most frequently asked examination questions. We're still revolving around Arene chemistry because Arene is some of the key chapters that most students are facing problem. So we are creating more frequently asked exam questions around this topic. But of course, if you have topics that you feel that you have difficulty on, questions that you have problem, well, feel free to send it to us. Or some of the questions that you see in A-level exam or H2 chemistry. So we will let go through as well. So today the series is focusing on one of the killer question that was set in the year 2016, paper 3, question 3d in GCE A-level examination, specifically H2 chemistry. So let's take a look together on this question. So this is a very long questions. So the first one they say that hot concentrated potassium manganate 7 oxidizes several classes of organic compounds to ketones, carboxylic acid and carbon dioxide gas. By this means, the structured compounds can be determined. Some compounds are easily oxidized while others require longer heating. So the following two schemes show some reaction of F, K, and of their oxidation product. So they tell you the reactions here, then followed by they want you to predict what are all the intermediate that is missing, the G, the H, the J, the I, the L, the H. So these kind of questions are normally people get freaked out. Okay, they can't really do the questions. They find it very difficult. So that's why this topic here I'm going to show it to you how easy it is for you to dissect the questions and get the final products. Right? There are some tricks involved to actually learn from it. So without further ado, let's take a look at the breakdown of what the question wants us to do. So let's take a look at number A. So compound F effervesces with sodium metal but does not react with warm acidified potassium dichromate 6. So explain this observation. So the first thing you must know is what is the purpose of them mentioning the word sodium metal. So sodium metal is targeting two groups. First group is hydroxy group, which means alcohol. Second is targeting carboxylic acid. So in other words, they're trying to tell you that this group here may have carboxylic acid, may have OH. Alright, so may have these two. So how do we confirm which one of them is present? Very simple, we go up. So we go and check out on our F here. Now F, how many oxygen do you see? Only one. So which means that there is no carboxylic acid. Simply there is only your alcohol group. So number 2, we can safely cross out. Okay, so now we know that this is actually an alcohol group present. Very good. But it doesn't tell us much because alcohol got primary, secondary, tertiary. So we check out the next information. So but does not react with warm acidified potassium dichromate 6. So what does it mean? That means that it cannot go through oxidation. Now, what is the alcohol that cannot go through oxidation? Only one. That is your tertiary, which is also known as your third degree alcohol. Right? Only your third degree alcohol cannot go through any form of oxidation. So right now we're going to explain this observation. So I think basically we explained already. So let me write down the key point. So the first one we can deduce is there is a presence of a tertiary, or what we call a third degree alcohol. Why are we so sure it can is a third degree alcohol? First thing, it can react with sodium metal. And what does it give you? It gives you effervescent. The effervescent is your hydrogen gas. Right, that's part 1. Second, it doesn't react with warm acidified potassium dichromate 6. So meaning that it will actually no oxidation for third degree alcohol. Alright, so this is your part A. Okay, this is the solutions. So remember the video here is served to let you understand the concept and how you solve it. I give you the answer, how it exactly looks like. But however, when I put in the keywords, there's a different part of the story. So we're focusing more in terms of solving in this YouTube channel. So let's take a look together on part number B. So for part number B here, suggest the structures of compound F to L in scheme 1 and 2. So this is the key part of the whole highlight of the questions. So this is very important skill that you need to learn. So let's take a look together on scheme 1. Now, most of you will find this very overwhelming. Wow, so many information. How am I supposed to do it? Now, there's not a lot of trick that you need to master. There's only a few tricks, right? Most of the people are very good in organic chemistry because they just know a few tricks and they become better. Now, if you learn the trick, you also be as good as them. So the first thing is you must remember some of the key molecular formula. I know some of you may say that my teacher never tell me to memorize the formula, but I will happily recommend one thing to you. Try to memorize certain molecular formula. This will give you an edge over the rest of the people. So the first formula I need to remember is C2H2O4. So whenever you see this molecule appearing, or this molecule has this exact molecular formula, I want you to be able to deduce that it is your oxalic acid. Right? Oxalic acid, right, also known as your ethane dioic acid. Right? This is another name, but you must remember, so this is the name and this is the formula, C2H2O4. So upon further oxidation, oxalic acid will give you CO2. There's a confirmation. Second thing you need to remember is whenever you see KMnO4, it will go through two different types of reaction. Vigorous oxidation, which is breaking your CC double bond, or side chain oxidation reaction. Now, if it's a vigorous oxidation, side chain oxidation reaction, whenever I see there's CO2 produced, right, just give me a good hint. Likely, right, is because maybe there is a terminal alkene present. And one terminal alkene only give you one CO2. So this is likely got 2 times terminal alkene. Alright, for those of you who are a bit unfamiliar with the word terminal alkene, it simply means that the alkene at the last position of the carbon. That's called terminal alkene. Alright, so you have this, this, and this. Now we take a look at the next part. So here, G, C4H6O5. Very difficult to say what kind of product is that. But I recognize this reagent and condition. Heat with concentrated H2SO4 is like concentrated H2SO4 has been known as a dehydrating agent. So meaning that they're trying to do what we call a elimination reaction. So they are removing water. So I suspect that in here, there's definitely CC double bond. Okay, 100% CC double bond elimination take place. And how do I confirm CH2 is removed? We can check the molecular formula. Currently from here to here, I think 2 hydrogen is missing and 1 oxygen is missing. Carbon remain the same. So it's confirmation that H2O is removed. So it forms CC double bond. Then after that, you have one more. KMnO4, it will cut the double bond. Remember I said before, KMnO4 is target vigorous oxidation, CC double bond cleavage, or side chain oxidation reaction with your benzene ring. So now we're going to cut it. Then you form maybe CO2. How come cut will give you CO2? This also tells you that it must have a terminal alkene. Alright, so in the first process of solving, you get a lot of bits and pieces of information. But this bit and pieces of information is very critical for you to find out the final product. So not all the time, the reaction that I say that you can think in a forward manner. Think in a forward manner meaning that you know what is F, immediately predict what is G. But in fact, most of the time you must work from the back to the front. So that means you must see, what's the final product? Then you slowly deduce based on the reagent, backwards all the way to the initial product. And that's what we're going to do right now. Because we have deduced what is this, because it's memorized, now I know that here is a terminal alkene. So I can roughly predict what is your I. Because you see I got 5 oxygen, got 3 carbon. There's not a lot of combination it can be. First of all, if you see a carbon with many oxygen present, I want you to think of one thing. Likely there is a carboxylic acid present. And you notice that for carboxylic acid to present, it always exists at which position? It's always at the end position, which means it can be either the extreme left or the extreme right. So there's only 3 carbon. And there's not a lot of way to arrange 3 carbon with carboxylic acid. It has to be linearly arranged. So currently you see you got 5 oxygen. So what does it mean? Maybe I think that, okay, one carboxylic acid is 2 oxygen, so maybe we have 1 more carboxylic acid. Then together we have 1 double bond O. Then followed by a check whether the formula is correct. So you go and check. You have 3 carbon present here, 2 hydrogen, and 5 oxygen. Okay, so we may say that, hey doctor, how do you figure out this one? It's very difficult, you know. I say, yes, I agree, this is difficult. However, elucidation questions, right, require you to predict with a little bit of gut instinct. At the same time, it can be logically predicted. So what did I notice here? I noticed that there's oxygen present here and there's a lot of oxygen. So the first thing come across my mind is carboxylic acid. So if I see maybe 2 oxygen, I predict maybe there's 1 carboxylic acid. If I see 4 oxygen, I'll predict maybe 2 carboxylic acid. Now is it always correct? No. But most of the time, more often than not, you can get the correct answer. Now, we predict this one already, it matched the molecular formula. Wonderful. But I must verify whether it's correct or not. So I go and predict what is my C4H4O4, which is your J. So I predict what is I already. Yeah? So to predict your J, remember we said before your J will have your terminal alkene because it go through your vigorous oxidation. So I go and think, Okay, so but where should I place the terminal alkene? So I go and check the formula. I got 4 oxygen here, so maybe the 2 carboxylic acid maintain because it's 1, 2, 3, 4. So which means that you have 4 oxygen remain. Maybe this is got 2 carboxylic acid. This is the one that giving the terminal alkene. So this is something come across my mind. So I'm going to write down J. Maybe this is how my J look like. It's a different color. Maybe this is CH2. Then you click off, and you still can form your final product. So but I also must verify whether it's correct or not. So let's check out. You have 4 carbon, 1, 2, 3, 4. You have 4 hydrogen, 1, 2, 3, 4, and 4 oxygen. And this looks logically correct. Now we're going to think backwards to your G. So now we're looking at G now, G. So for G here, how do we think it? Now remember, you're removing H2O. So if you are removing H2O in this case, then I try to think of, okay, can I add back the H2O, right, into the reactions? So there are 2 ways to add it. One way is you add a H here, then add a OH here. Second is add a H here, then add a OH here. But there's a criteria for this reaction. Because remember, we mentioned before, your F must be a, what kind of an alcohol? Because OH is alcohol. Is primary or tertiary? Is tertiary alcohol. Okay, it's tertiary alcohol. So I think that, okay, it's a tertiary alcohol. That means that I can predict my G here. Okay, my G here is likely going to be tertiary alcohol. So we're going to draw double bond OH, COH, then maybe CH3, then C double bond O and the OH group. Okay, a bit squeezy here, but you got an idea. So which means that here, let me just magnify it so everybody can clear on this one. So right down you have carboxylic acid, 2 carboxylic acid, 1 tertiary alcohol, CH3. Check the number of oxygen, 1, 2, 3, 4, 5. So it's 5, 6 hydrogen, 1, 2, 3, 6. Good. 1, 2, 3, 4, 4 carbon. So the structure is correct. So right now I predict, right, what is my G, then what is my H, then what is my J, what's my I. Now I'm going to assemble all of them together and predict what is going to be my F. So to predict what is your F, so an F here, what I'm going to do is maybe I'm just going to write on the right hand side. Okay, I'm going to write on the right hand side. So right hand side has a bit more space here. Okay, to predict what is F, you're going to draw out GH out. So you can have a good idea how this molecule is connected. So I'm going to draw out my G here. So my G, I can just go to put in the center of the structures. So this is OH, tertiary. Then followed by, you have your oxalic acid. Then you have 2CO2. Remember 2CO2 is what? Terminal alkene. Okay, terminal alkene. So you have 2 times CH2. So I'm going to draw 2 times of it. So now what we're going to do is we're going to assemble the molecule. But how do we assemble it? Remember just now we mentioned that this reaction here is likely to be a vigorous oxidation or side chain oxidation. So for your vigorous oxidation reactions, likely to be because there's no benzene ring. So what I'm going to do is I'm going to assemble the molecule by connecting this to the left hand side. Now you can also connect to the right, it's up to you because left and right is the same. So I'm going to connect these to one end. Then after that, I'm going to connect the CH2 to this end and this one to this end. And let me show you what I mean here. Let me do a highlight so you get a good idea. So right now, I'm going to connect this carboxylic acid here directly to this group. Okay, so this is the vigorous oxidation. You're thinking backwards. So this carbon and this carbon will join together to form a double bond. Then after that, let me use a different color. This carbon here, which have a double bond, will join to the CH2. So which means you connect them together, then you form your brand new CC double bond. Then after that, you still got one more last group. This double bond here will connect directly to this CC double bond to form the final product. Well, it looks a bit confusing, so let me show you how I get the final structures. So get the final structures here, I will draw out this here. Okay, sorry, let me use a different color. So let me just draw here. Let me use a red color. So this is CH3. This is OH. then followed by, remember the right hand side, we begin the easier one. The right hand side here is joined to this CC double bond. So I'm going to draw C double bond CH2 NH. Okay, so we're talking about this one joined to here. So recall, if you cleave the double bond, you get double bond O, H become OH, this becomes CO2. Perfect. So this one works. Now we're going to join this part to here. So we're going to draw this one. C, then you would draw a H here, then you join together with this C, a double bond group. So which means that this double bond O join to this one to become CC double bond. Then the OH will become a H here. Okay, the OH represent this OH, become a H here. Then you continue with the bond, then this one will be a C here. Then you will have a double bond. Why you have a double bond here? Because this is joined to another terminal alkene. So from here, you draw a H, then you draw a CH2. Then you go and verify whether this is correct. So you see, this one is a double bond, you cleave it, CO2. Then followed by you give a carboxylic acid here. Cannot be oxidized, you cleave it away, carboxylic acid, and this one will give you cut, carboxylic acid, you cut it again, you get another carboxylic acid. So this is what we call the oxalic acid derivative. And you cut this bond away, you get CO2 and H2O. So you complete the whole structures here to give you your final product of your F, right? A very complicated structures. Then you must double check whether the molecular formula makes sense. If you check the molecular formula out, you realize that this molecular match up. So this is basically your compound number F. So we solve all the structures here. Let's go to scheme 2, shall we? Okay, scheme 2. So we still have scheme 2 here. Now for scheme number 2, okay, this one we have a KMNO4 to form these reactions. You see this molecule here, C2H2O4. This is your oxalic acid. So we're going to draw the oxalic acid now. And how do I know? This is a memorized structures. Okay, memorized one. So oxidize to give you CO2, this is double conformation. Then you may think that, okay, so how is this and this connected? Oh, this is easier, you can work from here to here. So this is what I need to do when you do an intermediate transition state. What am I intermediate? Let me show you. So we're going to deduce what is your K. So this one, let me just draw OH, double bond O, then you have a double bond O here. Then followed by you have a oxalic acid, double bond O, OH, and C double bond O and OH. Now whenever you join the bond, the keep in mind is this double bond O will join to this double bond O because it's a vigorous oxidation reaction like consistent to what you see above. The same also apply to this. This will join directly to here to form the CC double bond form. So what I'm going to do is I'm going to draw the structures by simply delete away the oxygen. So I'm going to delete the oxygen away here. Okay, let me delete this. Okay, let me just delete the whole thing. So I'm going to join them up. Okay, so when you join them up, then you will form a C join to this C double bond, and this C here will join to this C for the double bond. Okay, remember, you join the C to the double bond, then the H here, and the H here, and the H here. Okay, so this is the overall structures of the molecule for your K. So let me just delete with this one to avoid any confusion. This one, there's no red line. Okay, so this is your compound number K. And you verified it. You have 12 carbon. So 6, 7, 8, 9, 10, 11, 12. There's one more carbon here. Calculate the hydrogen. It should be match up. Okay, now finally we go to the last one, your L here. Okay, your L. Now, so how to solve your L? So what I do is like that. You remember I said before, you have a lot of oxygen, you think of carboxylic acid. So now it's a bit strange. You have 6 oxygen. Now for 6 oxygen, how many carboxylic acid do you suspect to have? I suspect there will be 3 because one carboxylic acid got 2 oxygen. So I think that maybe this carbon you see here, right? This carbon you see here, will go through side chain oxidation reaction. So this is what I predict. So I'm going to draw the structures out. So you draw a benzene ring, then you draw COOH, then you draw another COOH, then finally COOH. Right? So this is your L group. Right? That's basically complete out the entire structures. So check the molecular formula, all makes sense. Then some of you may ask me, why is there a CO2? Because if you count the number of carbon, this L here short of one carbon from here, because this carbon here, you see, missing, go become CO2, right? It's side chain oxidation. Then number C here, state the type of isomerism that exhibit in compound F. Let's take a look, what is compound F? Right, this is our compound F. So compound F, first of all, we check together, there are two different types of stereoisomerism. There could be enantiomerism, which is a chiral center. There could be cis triisomers. So let's check which one actually exists. I check this one. This one here. Do you think this carbon here is a chiral or non-chiral center? Right, it's a chiral center because you have 4 different substituents. So you have one chiral because this is one substituent different from this. This is different from the rest, one chiral. Then at the same time, is there a CC double bond? I think a lot of CC double bond, but this is the cis trans isomerism. Because the left and right they have totally different groups. So you see, this H and H is opposite, is trans. You also can put the same side, becomes cis. So there are 2 different isomers. So right now we got 2 type of isomerism. So that means you can write down, one is called your enantiomerism and cis-trans. Okay, cis-trans isomerism. Then what is the total number of stereoisomers? You will use the formula 2 to the power of m plus n, because your m here represent your chiral, your n here represent your cis-trans. So this is 2, 1 plus 1 will give you 2 to the power of 2, 4. So total 4 isomers. Move on to the last one. Now, there are 2 isomers of K that will give compound L on prolonged heating with K-4. Draw the structure of these isomers and name the type of isomerism exhibit. So right now we have K. So maybe let me just draw the K structures. I think just now we determined what's K already. This is this. Then let me just refer to the up. Okay, let me just check. Okay, K here. Okay, so let me just draw the skeleton. Okay, so here, that means that this one here should be a double bond, and this one. Right, this is one isomers. So another possible isomers that will give you the same product as L. So I think that maybe it's this one. Okay, you just get the same product after oxidation. So maybe you can predict that you purposefully change the position of this carbon. Okay, because you see, if you change the position here, this one can go through side chain oxidation reaction as it still have your hydrogen. Okay, you still go through your side chain oxidation reaction or vigorous oxidation reaction to give you the final product. So this is the 2 isomers. Now, then what is the name of these isomers? There are many names, but I think one of the key names that you can say is you are simply changing the position of the carbon. So I call this as the structural isomerism. You also can call this as a constitutional isomerism. Some of you want to be even more specific. It's actually called a chain isomerism, but nevertheless, we just call it a generic form, structural isomerism. Then that will do. Alright, I hope you have enjoyed these videos. So please put a comment here on the video below so that you can give me some feedback on the video. Then followed by some of the questions that you think that you may have problem that I will definitely like to discuss with you. So thank you so much for watching it. So give a thumbs up if you like it, and see you next time.